This is 8-5, day number 2. We're still solving trig equations. Remember, the book's trying to intimidate us and calls us section 5 more difficult trig equations, and I've been trying to make my case that I don't think they're more difficult. They're just we're looking at some different cases that we haven't seen before. Some involve some trig identities. Some don't. Some involve a squared term. Some don't. We're kind of taking our repertoire of skills and the type of trig equation that we can solve, and we're trying to broaden it up a bit. All right. What you'll see in some of these examples today are some cases where a couple different things go on. In this first one, I say I have two different trig functions. That's never a fun situation. Trig equations are really, really hard to solve if we're not all in terms of the same function. But we talked in the first day about how you can't always divide by a trig function when you're solving because you might lose some solutions. In 5, we can. And I'm going to do 6 right after this and illustrate a case where we can divide by a trig function and one where we can't. And then I want to talk about why there's a difference. What works out really nice here is when I divide by sine, that cancels on the left side, just leaving the 2, and on the right side we have cosine of x divided by sine of x. Well, this just works out perfect, because cosine over sine, that's cotangent. That took care of the problem of having two different trig functions, as now I just have cotangent. And the easiest thing to do here would be to use a reciprocal, switch that to 1/2, and switch my trig function to tangent. Okay? And 1/2 is not a tangent value that we find on the unit circle, so I'm going to have to go make sure my calculator is in radian mode, and I'd have to go do an inverse. Inverse tangent of 0.5 is 0.46. But remember, we have a little rule for tangent to generate solution number 2. We take pi and we add the first solution that we got. And there we get 3.61. So 0.46 radians and 3.16 radians would be the solutions to that equation. Let's look over at 6. We have sine squared of x equals sine of x. This is kind of a tricky one to do. And the first thing I would do at this point is subtract by sine of x, so that on the right side we get 0. On the left side we'll have sine squared x minus sine of x. Okay, what I'm going to do now is take the left side and I'm going to take out a common factor of sine x, leaving sine squared with just a remaining factor of sine x. And the second term, which was just sine x, is now -1. Because I factored at that case, in this case, this is a point where I should not divide by the sine of x. Okay, that's where 5 and 6 are different. Here, when I divided by sine of x right off the bat, I hadn't done any factoring. And if that's the case, if it's one of the first things that you're doing is to go ahead and divide by a trig function, you're typically okay to do it. That's why it was fine for number 5. Here we can't because we'd lose solutions. Instead, I take each factor individually and set them equal to 0, which would leave us with 2 equations to solve instead of 1, but after we factor, they're typically equations that are shorter and a little bit easier to solve. Should be thinking unit circle first before going to the calculator. 0 is a sign value that we find on the unit circle. 0 and pi. Those are 2 angles that have a sign value of 0. And sine is 1. This is a rare little case where we only get one solution. That would be at pi over 2. It's the only place between 0 and 2 pi where sine is 1. Okay, but that's the only place. Only place on the whole solution, on the whole unit circle that has that solution where sine is 1. All right? Again, 2 cases, one where we can divide by a trig function, the other we can't. Anytime it involves factoring, no dividing by trig functions. Let's take a look real quick here at 7. We see another case where we have 2 different trig functions, which again, it's not good. We don't want that. We want it to get them to be the same. And on the first example that I did, I divided by sine, and then it worked out that the right side was cosine over sine. Here, that it's not going to work like that. If I were to divide, I'd have cotangent over cosecant. Doesn't seem like a great route to go. What I do have, though, is some trig identities, and we should always be conscious of our trig identities. And at any point that we think it would make sense to do so, we should do some substitutions with those identities. For example, there is an identity that says that cosecant squared is equal to 1 plus cotangent squared. And then the right side will still just remain 3 cotangent squared minus 1. Okay, now it seems like the equation got even more complicated here for a second, but in reality it hasn't. Largely due to the fact that it's all now in terms of cotangent, which is a good thing. That's going to be useful to have it all in terms of one trig function. Okay. What I would do next on the left side is distribute the 2. And I would have 2 plus 2 times cotangent squared. And that equals 3 cotangent squared of x minus 1. Now I'm just going to move some terms around to kind of get this all arranged properly and set up the way I want it. First thing that means is subtracting 2 cotangent squared, which just leaves cotangent squared minus 1 equals 2. Next step would be to add 1. And we get that 3 equals cotangent squared. Okay? Cotangent isn't typically a ratio that I like working with in terms of its inverse. My preference would be to flip the 3 and make it a 1/3. And now deal with tangent. Okay? What I've got to do now is take the square root and what I will have on the left is plus or minus the square root of 1/3 equals tangent of x. Now this can be a little bit tricky because what I need to do right now is I need to be thinking about do I use the unit circle? Because this is the point here where I do inverse tangent, because that's all I have on the right at this point. It's just inverse tangent. What I need to think about is the square root of 1/3 on the unit circle or not, because I should go there and get exact answers first if I can. Okay, now I haven't fully simplified the square root of 1/3, so I should do that before I move on. So this would be plus or minus the square root of 1 over the square root of 3. That would be the same as 1 over the square root of 3. And then as I rationalize this, we end up getting plus or minus square root 3 over 3. Okay? That's a little bit tricky to tell, but because I mean, if I kind of clear all this mess up I have on the bottom, we have tangent of x equals plus or minus square root 3 over 3. Question now becomes, is that a key point on the unit circle? Okay. And it's not necessarily super obvious, but it is. Okay. It is. And it may not be a bad idea, whatever unit circle you've been using, to go through and label tangent values. Because tangent is y over x, so we can use the coordinates on the unit circle and divide them to get tangent values for each angle, but that's kind of annoying to have to do that over and over again. It's a good idea to do it once and then just write those on there. 30 degrees has a tangent value of square root 3 over 3. 150, it's negative. 210, it's positive. And the very last solution would be 330. Okay. Those are your 4 angles that would satisfy the equation that we're looking at here. Here is number 8. Okay, a lot going on this one. We have 2 cosine squared of x minus cosine of x. And what I think we will do with this one is, as far as examples go, call it quits. I think this would be a great one for you to look at on your own. If you have any questions on this one at all, obviously let's talk about those more in class. But a couple pointers here on this one. It's got that cosine squared. Okay, that's something we have to look at, cosine squared. And 2 minus secant. All right. We got 2 different trig functions, so that's the approach that you should take. Should deal with that right away. That we can't make a lot of progress solving this equation if we have cosine and secant. So at some point, preferably earlier rather than later in the process of solving, we need to get all this on the same page and get it all in terms of one trig function. All right, but that's the last example we have. Give it a shot. See if you can put some time into that one and figure it out. And if you can't, let's bring it up in class and let's talk more about it then.